Alright, welcome to the lunchtime video. So I missed the lunchtime video yesterday. There is some good news in that I'm going to have a bit more time to study for the test than I had initially thought. But still, time is definitely the most important resource I have. And it's really rapidly running out. So where I left off in the last video, I had RSVP bandwidth constraint configuration. I moved on to the next topic. I'm just going to do a quick check to make sure that I uploaded that video. Okay, so and it looks like I didn't even upload the video from last time. RSVP bandwidth constraint configuration. Oh, okay, it looks like I did. RSVP bandwidth constraint configuration. So, yep, that was last time, that was the first video. So I don't remember exactly what I did with that. I'm just going to watch the last part of it. Oh, it looks like I was doing an exercise here. Oh, yeah, okay, so I remember what that was. So, yeah, that was this basic LSP configuration here with those queues and everything like that. So I'm not going to include that in the notes of this next video here that I'm working on right now. So let's move on to the next document. Let's just read about Cspf. Now it's not necessarily specific to RSVP bandwidth constraint configuration, but Cspf I think will be important to learn about. So this is LSP computation, constrained path LSP computation. The constrained shortest path first Cspf algorithm is an advanced form of the shortest path first SPF algorithm used in OSPF and ISIS route computations. Cspf is used in computing paths for LSPs that are subject to multiple constraints. When computing paths for LSPs, Cspf considers not only the topology of the network, but also the attributes of the LSP and the links, and it attempts to minimize congestion by intelligently balancing the network load. The constraints that Cspf considers include LSP attributes, administrative groups, that is, link color requirements, bandwidth requirements, explicit route, strict or loose, hop limitations, priority, setup and hold, link attributes, administrative groups, that is, link colors assigned to the link, reservable bandwidth of the links, static bandwidth minus the currently reserved bandwidth. The data that Cspf considers comes from the following resources. Traffic Engineering Database provides Cspf with up-to-date topology information, the current reservable bandwidth of links, and the link colors for the Cspf algorithm to perform its computations. A link state IGP, such as OSPF or ISIS, with special extensions is needed. For Cspf to be effective, the link state IGP on all routers must support the special extensions. While building the topology database, the extended IGP must take into consideration the current LSPs and must flood the route information everywhere. Because changes in the reserved link bandwidth and link color cause database updates, An extended IGP tends to flood more frequently than a normal IGP. See Figure 1 for a diagram of the relationships between these components. Currently active LSPs includes all the LSPs that should originate from the router and their current operational status, up, down, or timeout. So CSPF takes in link attributes and it takes us LSP attributes, and then it is used for LSP paths, RSVP signaling. Okay, I guess I don't really understand this too much. This is just the relationship between the components of CSPF, but maybe that will make sense by the time I finish reading. So this section discusses the following topics: how CSPF selects a path, CSPF path selection tie-breaking, computing CSPF paths offline, how CSPF selects a path. To select a path, CSPF follows certain rules. The rules are as follows. Number 1, computes LSPs one at a time, beginning with the highest priority LSP, the one with the lowest setup priority value, among LSPs of equal priority. CSPF services the LSPs in alphabetical order of the LSP names. Number 2, prunes the traffic engineering database of all the links that are not full duplex and do not have sufficient reservable bandwidth. Number 3, if the LSP configuration includes the include statement, prunes all links that do not share any included colors. Number 4, if the LSP configuration includes the exclude statement, prunes all links that contain excluded colors. If the link does not have a color, it is accepted. Number 5, if several paths have equal cost, chooses the one whose last hop address is the same as the LSP's destination. Number 6, if several equal cost paths remain, selects the one with the fewest number of hops. And number 7, the last one, if several equal cost paths remain, applies the CSPF load balancing rule configured on the LSP, least fill, most fill, or random. CSPF finds the shortest path towards the LSP's egress router, taking into account explicit path constraints. For example, if the path must pass through router A, 2 separate SPFs are computed, one from the ingress router to router A, and the other from router A to the egress router. All CSPF rules are applied to both computations. CSPF path selection tie-breaking. If more than one path is still available after the CSPF rules, how CSPF selects a path, have been applied. A tie-breaking rule is applied to choose the path for the LSP. The rule used depends on the configuration. There are 3 tie-breaking rules. Random, one of the remaining paths is picked at random. This rule tends to place an equal number of LSPs on each link, regardless of the available bandwidth ratio. This is the default behavior. Least fill. The path with the largest minimum available bandwidth ratio is preferred. This rule tries to equalize the reservation on each link. Most fill. The path with the smallest minimum available bandwidth ratio is preferred. This rule tries to fill a link before moving on to alternative links. The following definitions describe how a figure for minimum available bandwidth ratio is derived for the least fill and most fill rules. Reservable bandwidth equals bandwidth of link times subscription factor of link. Available bandwidth equals reservable bandwidth, which equals bandwidth of link times subscription factor of link minus sum of the bandwidths of the LSPs traversing the link. Available bandwidth ratio equals available bandwidth divided by reservable bandwidth. Minimum available bandwidth ratio for a path equals smallest available bandwidth ratio of the links in a path. Note, for the least fill or most fill behaviors to be used, the paths must have their bandwidth specified using the bandwidth statement at the edit protocol's MPLS label switched path LSP name hierarchy level, or minimum bandwidth specified using the minimum dash bandwidth statement at the edit protocol's MPLS label switch path LSP dash name auto bandwidth hierarchy level, configured to a value greater than 0. If the bandwidth or minimum bandwidth for the paths is either not configured or configured as 0, the minimum available bandwidth cannot be calculated and the random path selection behavior is used instead. Computing Cspf paths offline. The Junos OS provides online real-time Cspf computation only. Each router performs Cspf calculations independent of the other routers in the network. These calculations are based on currently available topology information that is usually recent but not completely accurate. LSP placements are locally optimized based on current network status. To optimize links globally across the network, you can use an offline tool to perform the Cspf calculations and determine the paths for the LSPs. You can create such a tool yourself. How do I do that? Or you can modify an existing network design tool to perform these calculations. You should run the tool periodically, daily or weekly, and download the results into the router. An offline tool should take the following into account when performing the optimized calculations: all the LSP's requirements, all link attributes, complete network topology. That sounds like a pretty heavy lift. Configuring Cspf tie-breaking. When selecting a path for an LSP, Cspf uses a tie-breaking process if there are several cost-equal paths. For information about how Cspf selects a path, see how Cspf selects a path. You can configure one of the following statements. You can only configure one of these statements at a time to alter the behavior of Cspf tie-breaking. By default, a random tie-breaking rule for Cspf is used to select a path from the set of equal cost paths. However, you can also explicitly configure this behavior using the random statement. To prefer the path with the least utilized links, include the least fill statement. To prefer the path with the most utilized links, I don't understand why you would want that one, include the most fill statement. I would think you would always go with the least utilized links. Disabling constrained path LSP computation. If the IGP is a link state protocol such as ISIS or OSPF and supports extensions that allows current bandwidth reservation on each router's link to be reported, constrained path LSPs are computed by default. The Junos implementations of ISIS and OSPF include the extensions that support constrained path LSP computation. ISIS, these extensions are enabled by default. To disable this support, include the disable statement at the edit protocol's ISIS traffic engineering hierarchy level, as discussed in the Junos OS routing protocols library. OSPF, these extensions are disabled by default. To enable this support, include the traffic engineering statement in the configurations of all routers running OSPF, as described in the Junos OS routing protocols library. If ISIS is enabled on a router or you enable OSPF traffic engineering extensions, MPLS performs the constrained path LSP computation by default. For information about how constrained path LSP computation works, see constrained path LSP computation. Constrained path LSPs have a greater chance of being established quickly and successfully for the following reasons. The LSP computation takes into account the current bandwidth reservation. Constrained path LSPs reroute themselves away from node failures and congestion. When constrained path LSP computation is enabled, you can configure the LSP so that it is periodically re-optimized, as described in optimizing single LSPs. When an LSP is being established or when an existing LSP fails, the constrained path LSP computation is repeated periodically at the interval specified by the retry timer until the LSP is set up successfully. Once the LSP is set up, no recomputation is done. For more information about the retry timer, see configuring the connection between ingress and egress routers. By default, constrained path LSP computation is enabled. You might want to disable constrained path LSP computation when all nodes do not support the necessary traffic engineering extensions. To disable constrained path LSP computation, include the no Cspf statement. Oh, okay, so that's interesting. So okay. For a list of hierarchy levels at which you can include this statement, see the hierarchy statement summary section for this statement. If you disabled constrained path LSP computation on LSPs by configuring the no Cspf statement and then attempt to advertise other LSPs with lower metrics than the IGPs from this router in either ISIS or OSPF, new LSPs cannot be established. Okay, so that was kind of eye-opening. I mean, obviously I was barely paying attention to what I was reading because it was so dry, but I'm pretty glad to have read it because I definitely encountered a lot of issues with CSPF. Alright, let's take a look at the INET 0. Okay, so this is imposing bandwidth constraints. The previously configured TE metric has been removed from the configuration. We now want to signal an RSVP LSP and influence the path by manipulating the available bandwidth. Okay, so this looks really good. Let's do this with the lab and hopefully get this working. So let me open up, here we go, we've got GNS. So we're going to be manipulating the LSP by way of bandwidth. So let's start off by taking a look at our version of that command. So I'm going to do root clouds, there we go, show configuration, display set pipe no more. So we've got a label switch path there. Let's take a look at it. Show database extensive 0.7. Okay, so gonna have a similar as what they've got. It looks like they're using ISIS. We're gonna use OSPF. Now I am curious if I've got OSPF traffic engineering enabled on my provider routers. I think I do. Yeah. By altering the TE metric, we only alter the cost of the link for calculations done by the CSPF algorithm. We can verify this by looking at the information in the TED. We look at the information stored in the TED by issuing the following command. The metric that is listed first is the TE metric. Okay, so I don't see, I wish they would highlight this, because I don't see the TE metric. Oh, is this it? Oh, no, it looks like they do highlight it. So they've got metric and IGP metric. But on mine it looks like I've only got metric and static bandwidth. I don't have the IGP metric as well. Probably because I'm using OSPF instead of ISAS. I can switch it over, but it's just kind of a lot of work. The metric that is listed first is the TE metric. This metric was used for the Cspf calculations. The IGP metric used to calculate the routes in the inet.0 table remains unaltered. So I don't have a IGP metric for some reason. Let's just pipe match. Okay, so yeah, I don't see anything that says IGP metric. As an alternative to the show TED database extensive command, we could have also used the show ISIS database with the extensive option to verify the same thing, or show OSPF database opaque area extensive when running OSPF. So yeah, this looks like the same thing. Let's see if we've got the IGP metric in here now. I still don't see anything. So let's try to filter it out in case my eyes are failing me. Nope. Okay, so this is imposing bandwidth constraints. Yep, and then the next is using link colors. We'll skip that, so we'll just do this section, and then that might even be it. But before completely closing it out, we'll take a look at this final one that I had marked as interesting. But yeah, before I do that though, I'm going to take a quick break. I'll be right back though. Alright, so I am back and ready to continue. So this is imposing bandwidth constraints. The previously configured TE metric has been removed from the configuration. Now we want to signal an RSVP, LSP, and influence the path by manipulating the available bandwidth. By default, Juniper router allows you to use 100% of the bandwidth of an RSVP enabled link. In our scenario, all of the links are 1 Gbit. Alright, so I'm not sure what it is in my scenario. Let's find out. So same thing. They're all going to be 1 gigabit. Before imposing a bandwidth constraint on the LSP, we first reduce the available bandwidth on the link between R1 and R8. Okay, so in my case, let's impose that on the link between provider edge 1 and provider 2. So that's going to be GE002. Okay, so the command's going to be, oops, it's not going to be here, it's going to be edit protocols, RSVP, interface 002, it's going to be set subscription. Yep, so this is the link bandwidth percentage for RSVP reservation. And yep, so this is exactly what we went over in the last video. Perfect, so I feel like I'm really on target here. So let's set it to 89. The subscription configuration command reduces the available bandwidth from 1 gigabit to 890 megabits per second. And that's interesting that it's 890 because 89 is a strange, it's a really strange way to say 890 megabits. But let's commit that and then verify that the change has been made properly. Yep, so 890 megabits per second, perfect. And that's the available bandwidth. To demonstrate that we can use the bandwidth to control the path the LSP will follow, let's configure an LSP like this. Okay, so I already have a LSVP configured. So let's just modify the existing LSP. We're going to do set bandwidth on it. Bandwidth to reserve. The LSP was configured to reserve 900 megabits on every link. An LSP does not require any bandwidth by default. Because of the previous configuration, Cspf will only consider links that have 900 megabits or more of bandwidth available. As a result of this configuration, the LSP will not be able to traverse the direct link towards router 8. After the LSP is set up, we can observe the following. Okay, and that's because we set it to be below 900, we set it to be 890. So let's verify this. Okay, so we've only got one session. Here they've got 4 sessions, which is kind of interesting. Because of the imposed bandwidth constraint, the LSP was not signaled across the direct link. It took the following path instead. Okay, so let's so here's the path that it took, 192.168.12.2. So let's take a look at which interface this comes off of. Okay, so this is via 001. Yep, so that makes sense. Now let's add that bandwidth statement to this and see if we can push it over to 003. So it's going to be that subscription statement. Yep, right here under protocols RSVP. We'll add it to this interface, and now hopefully we'll see the LSP goes over this interface instead. Okay, so just as this one is no longer eligible, this one is not eligible either, and that is because we're only allowing links with at least 900 megabits available on them to be used in our calculations to build our label switch path, and we set the, artificially we set the value of the link to be used in the calculation regardless of what the actual value of the link is. Okay, so let's take a look, and hopefully it is going over a different path now. It might, yeah, so it's got to do re-optimization. Looks like it's going to take it 99 seconds to do that. So let's just do a pipe no more, pipe refresh. And we'll get a new printout every 3 seconds. So yep, so 98. Well, unfortunately that's like a minute and a half, so that's going to be quite a bit. But let's see what we can expect it to move over to. Okay, so it'll move over to .14.2. Right now it's at .12.2, but after that re-optimization timer has expired, which now it's less than a minute, really no time at all, it'll move over to .14.2. Another thing we can do is do a monitor start MPLS t-shoot and get some good details about what exactly is happening as soon as that re-optimization timer expires. So it looks like we got our regular notifications that happen when all is quiet. So I think around 5 seconds I'll just stop the capture here, and then we'll just focus on those messages, and then I'll come back and look at it afterwards. So 8 seconds. So yep, I'm gonna stop the. Yep, and now we can see here's all the messages. So I'll save these, put them in a notepad file. We'll look over them more closely after I've confirmed that it has jumped over to 14.2. So it looks like it's done. Gives us a nice simple message saying so. So I'm gonna save this so I don't lose it. Okay, perfect. Okay, and now I'm going to go back and make sure it jumped over to 15. Sorry, 14. Nope, so it's still at 12.2, which is interesting. I did not think it would still be showing 12.2 here. Okay, well, yeah, I wasn't expecting that. Let's go over the output. Let's see if 14.2 shows up in here, and it does. Oh, but it's just because of that. Let's do a normal search, not a regular expression. Oh, so 14.2 isn't on there. We are getting some messages saying that the links don't have enough bandwidth. Okay. Yeah, so it didn't switch over to 14.2 for the computed ERO. That's really not what I was expecting. I thought it would switch over here. So let's try to figure out why I did not have the correct expectations. And it looks like there's two computed. So there's a standby and there's the primary. So it looks like the standby is going through that. But I'm surprised there's a .4. I thought there was only a .1 and a .2. Oops, it's a loud noise. Let's see here. So, okay, well, let's just start off by looking at the configuration. Oh, and I do have a 1 o'clock meeting, so this is going to need to wrap up pretty quick. You know what? Let's get rid of the secondary, just the extra configuration. Let's simplify things. So we're going to be deleting link protection, and then, oh, you know what? This is probably it here, because, yeah, this is it here. It's forcing it to go that path for the primary, regardless of the calculations. And I think the calculations allow it to take whatever path it so chooses. So you can see the calculations are only applied to the secondary path. So you can see before I had that, it was probably not at .14. Unless it was. It probably was. Yeah, it was. But let's get rid of it. I think I figured out why it's behaving differently than how I expected. It's because of these extra commands. So let's remove them. Specifically, this one here, primary via P1. That's the command that really needs to go. Okay. Okay, so I think we're going to get, oops, so I'm still calling it somewhere. Let's take a look at the candidate configuration by doing show, oops. Okay, well, let's take a look at the active configuration then. Show configuration, pipe display set. So it's still showing up here. Let's get rid of that. And this is because it just deleted the knob. It just deleted the most specific part. It didn't delete the whole thing. So now let's do a show configuration. Yeah, and now we don't have that in there. So hopefully that command, I believe it was show MPLS, LSP, PE1, PE2. I actually forget what it was. Here it is. So now it's not even Computer, perfect. So yep, now it went through 14.4. So now if I remove the if I modify those limitations I had, now it will behave more predictably because I am no longer forcing it to go through a primary path with specific configuration down there. So let's set subscription 89 here, and just for fun, let's see it fail out. Just because it's the lab. Oh, but it's going to take us longer than I have. I only got 4 minutes. It looks like it's going to take more than a minute. One thing I might be able to do is force it to re-optimize. So if I do clear MPLS LSP all, okay, so that bumps it down to 30 seconds, which is a lot shorter. So we're going to see what happens when it tries to recomputate in 13 seconds. And I believe it will fail. Yep, it failed. Yeah, and 2 times, so it had already failed. But okay, so now let's remove this subscription 89 from this first link, and we'll see that will be the one that it chooses because that's the only one that's available, and it is good enough evidence for me that I understand what is going on. So let's do this, see how long it's going to take. It's going to take 112 seconds. That's a lot of seconds. So, actually no, it looks like it did it instantly, and it's just not going to re-optimize. So it happened instantly. It picked .12.2. Let's go back to configure private, show pipe display set, pipe no more, and then let's do a rollback 1. Show pipe display set, pipe no more. Okay, and now let's delete it from here. Okay, and now we'll see that it goes through the 14.2, and that will be the last video, or that will be the end of this video. I have a meeting at 1. So, yep, now let's look at that again. Oops, and it's through 12.2 again. There we go. After I cleared it, it did it automatically. It found out. So it would have probably, after the recomputation, would have switched it over, but I did not have that much time to sit and wait. Alright, so thanks for watching, and I'll see you in the next one.